Hello, and welcome to Empowered Learning. This video will be about definite integrals, and in particular about using Riemann sums as well as known geometric shapes to find out what a definite integral is for a particular function over a closed interval of x values. So let's go ahead and get started. So the first thing that we see here is the definition of a definite integral, written as a theorem. So it says, let f be a continuous function. That means a function without any holes, gaps, discontinuities, vertical asymptotes, anything like that, over some closed interval of x value, starting at some x value a and going to some x value b. And then it says, then the Riemann sums, which is, if you've seen my previous video about areas on the curve of a function, then you'll know that the Riemann sum is just a sum of a bunch of little rectangles that we're trying to stuff under the curve of the graph in between wherever that graph is and the x-axis. Okay, so then the Riemann sums for f on that closed interval approach some real number limit, and we're calling that I as n approaches infinity. Okay, so essentially, what this is trying to say is that if we can use the infinite sum, and that's why you see this limit I of the Riemann sums for f on the closed interval from a to b is called the definite integral. So really what we're saying here is that if we do the limit as n approaches infinity of sum of f of x sub I times delta x, if we do that, then this portion here we could call the infinite sum, which we are then using the integral sign for that over the range from a to b. And so from there we can find out what's called the definite integral, which is just another representation of the area under the curve of a function from x equals a to x equals b. And we notice here that whenever we have our notation here for the definite integral, then the integrand is what f of x is, the lower limit is a, upper limit is b, and of course this dx here is our theoretical width for our rectangle here, if that width is as small as it can possibly be. All right, so let's go ahead and move on. So what we see here is that whenever we talk about interpreting the area under a curve for a definite integral, we are specifically talking about the area under the curve from wherever the curve is to the x-axis. And so we interpret the area that is from the curve to the x-axis that is above the x-axis to be positive, and if that area lies below the x-axis, then it is negative. And so in noting that, if we were to have to do compute the definite integral of the area under the curve from, let's say, a to b here, and let's say we had some middle x value here, and I'll call it c, then from a to c would be interpreted as a negative area, and from c to b would be interpreted as a positive area. So this is just a quick example here. So let's say we knew that the area under the curve from A to B right here is negative 3.5, and the area from B to C is going to be 12. Then we would take what's called the net area of what is above and what's below. And so we would see that total area, or total net area under the curve is 8.5. All right, so where are we trying to go with all of this? So we know that from the previous videos that if we do the summation of those little rectangles from x equals a to x equals b, the more we try to stuff in between that little small open interval, closed interval of x values, the more tedious that it gets, okay? And so whenever we can, we try to use well-known geometric shapes to do that instead of trying to calculate the Riemann sum. However, what we're trying to work to is to get to a point to where we have some pre-made formulas and just an easier way to be able to do this than just doing iterations of adding up areas of rectangles again. Okay, so in short, we will be using the following toolboxes in studying integral calculus here. And so I'm reading that from this sentence right here. And so again, like I was saying, we eventually don't want to go through the tedious task of computing areas in well-known geometric shapes and Riemann sums. Okay, so we're going to study some basic properties of integrals now that we know what that operator is. We're going to look at some shortcut formulas for specific types of functions, as well as specialized integration techniques to help us out. And we're going to look at the fundamental theorem of calculus. And so this is going to be a video series, so you'll see that the fundamental theorem of calculus is going to be another video that I'm going to do for you. Okay. Now, right now, we're going to be in toolbox 1. So in other words, we're about to look at some basic properties so we know how to operate with this new operator that we've just learned. Okay. And so we will start, excuse me, we will start looking at some other shortcut formulas, some specialized integration techniques, and the fundamental theorem of calculus a little bit later. So I'm going to go ahead on and skip this next page here. And these are the basic rules for definite integrals. And so number 1 basically says that here, if we have our limits of integration out of order, to be able to put them back in, we have to multiply everything by -1. And of course, the assumption here is that with the limits of integration, A is less than or equal to B. And we're also assuming that the integral, or the area under the curve of f of x dx, we're assuming that this is greater than or equal to 0. Okay? Meaning that we're looking at the function from wherever it is down to the x-axis. And of course, if it's opposite of that, we would have to append the negative on there, like we talked about a few slides earlier. So number 2 basically says if the limits of integration are the same, then we basically have a rectangle with width 0, and thus we have no area. The constant multiple, just like we know with summations as well as derivatives, if we have some function being multiplied by some non-zero constant and we need to perform the integral to it, we can pull the constant out. The sum and difference properties basically say if we want to know what the definite integral is of the sum or the difference of two functions, then we can just evaluate the definite integral of each separately and then either add or subtract those answers. So number 5 talks about the example I gave to us previously, and I'm going to go back to it so that you remember what I was saying. So here it's saying that, hey, if I basically want to do the integral from A to C, then I can do the part from A to B first, and then add to that the part from B to C. And so that's essentially what property number 5 is saying. Property number 6 is letting us know that if we don't necessarily know how much area is under the curve here, one thing that we can do is we can use constant functions to say, all right, well, we know that it can't be below this amount and it can't be above that amount. Okay, and we're going to actually see some examples on how we use this particular inequality property. And of course, the last property says that if my function f of x either lies above or intersects g of x, somewhere on this closed interval here, then we know that the area under the curve for f of x is going to be interpreted as being larger than or at least equal to g of x on that closed interval. Okay? And of course, here, just like I said before, we're assuming that if f of x is above or on the x-axis, and that's what the f of x is greater than or equal to 0 means, then that also means that when we find the definite integral, or the area under the curve of f of x from x equals a to x equals b, we consider that area to be non-negative as well. And so these are just sort of visual depictions of what most of these properties are talking about here. So this is our zero width interval. We see the constant multiple. So we know that if we take the definite integral of f of x, we can just multiply that by 2 and get what that is if 2 is the constant. Here we know that if we want to find the area under the curve of both of these, we can just do the area under the curve of f of x and of g of x and just add those together, or subtract those as needed. Okay? Add the additivity, so we do the area under the curve from a to b and then from b to c. And this is what I was talking about when we did the min-max inequality. You see here that this is a constant function, and everything that's in the green would be the area under the curve of the minimum of f. And here would be constant function at a max. And of course, what the area under the curve of f of x is actually in the middle of that. And then of course the last one here, if f of x lies above or is equal to g of x over some interval, closed interval of x values, then the area under the curve of f of x should be larger than or equal to g of x. All right, so here, for those of you that are studying calculus, this is just a basic table of integrals, and so indefinite integrals, I should say, and we'll use this. So nothing important here. You can always find another table of integrals online somewhere, or if you have a calculus book, it should be a table of integrals in there somewhere. So just wanted to kind of quickly scroll through these. If you don't have those resources, you may want to pause the video and copy these as needed. But essentially here, if you know the derivatives of most of these functions, then you'll be able to produce the indefinite integrals as well. All right, so now let's go ahead and move on to this example. And so what we're wanting to do here is basically find the area under the curve of x cubed minus 3x. And you see here that we're considering the interval from 0 to 3. And we want to calculate what the Riemann sum of f of x would be from in between 0 and 3. And we want to use 6 rectangles to do that. Okay? Now, we're going to do this, but our next step, and I'll go ahead and show you that now to kind of show you where we're trying to go. Our next step is to take this function here and now do the limit as n approaches infinity of that, which basically means what we're trying to do in this step here is find out what the definite integral is. Okay? But we're just doing it by using Riemann sums. All right, so let's first go ahead and find out what the approximation or the estimate of the area under the curve of f of x is when we use only 6 rectangles. So first thing that we want to do is, since we know that if we're doing, let's say, right endpoints to sample, we need to figure out what our delta x is, and we need to figure out what our sub-interval endpoint values are. So our delta x is b minus a over n, where a is 0, b is 3, and our n here is 6. So that will just be 3 minus 0 divided by 6. So that's just 1/2. Now, we also know that when we find out what our x of I values are, everything can be modeled by x of I is equal to a plus I times delta x, which in this case is going to be 0 plus I divided by 1/2. And so basically we're going up in units of 1/2. So x of 0 would be 0, x of 1 would be 0.5, x of 2 would be 1, x of 3 would be 1.5, x of 4 would be 2, x of 5 would be 2.5, and x of 6 would be 3. And since we're using the rightmost endpoints, we're going to use all the points that are, I guess all the x values that are the rightmost ones. And so to make sure that we understand that the leftmost ones will be from x equals 0 to, x sub 0 to x sub 5. Whereas the rightmost will be from x sub 1 all the way to x sub 6. So we'll be using these. So for our right endpoint estimate using 6 rectangles, we'll use the summation from, let's say, I equals 1 here. Let me get that equal sign looking a little better. So I equals 1, and we'll go all the way up to 6 of f of x sub I times delta x. So now that we have that, we know that we would just be doing f of x of I for all these values from x of 1 all the way to x of 6, and then multiplying all that by delta x, since delta x, which is 1/2, is a constant function. Okay? So here we have f of x of 1, f of x of 2, f of x of 3, f of x of 4, f of x of 5, and f of x of 6. And of course, all of that would be multiplied by 1/2. Okay? So what I'll do is make a little room for that over here. Delta x equals, and just say 1/2 times all of that. Okay? So now what we can do is get these values for f of x. And so we know that f of x sub 1 is just 0.5, and then 1, 1.5, and 2, 2.5, and then 3. So come over here and write that now. That's 1/2 times f of 0.5, f of 1, f of 1.5. Didn't come out too well. Let's try that again. 1.5, f of 2, f of 2.5, and f of 3. And of course, at this point, you could use a calculator to figure out what all these values are. Not really that much to it. So what I would recommend you do now is to actually pull up a calculator, put that function into your calculator, and let it evaluate the values. So come here and bring this up, and we'll go ahead and do that. All right, so turn this on, and here, when we erase this, we say x cubed minus 3x. I do believe that is what we were working on here. Yep, minus 3x. So just want to make sure of that. And so now, of course, our window here from 0 to 7, that's good enough for what we're going to be doing, which is from 0 to 3 for the x values. So now we can just do second, trace, value, and then after that we can just start plugging in values of x here. So, alright, so at this point we'll just start plugging in values. So 0.5, it's not right. So 0.5, do that, we get value of negative 1.375. And so now we'll do the same thing at 1, get negative 2, and then at 1.5, and we get a negative 1.125, and then at 2, we get 2, at 2.5, we get 8.125, and at 3, we get 18. And so all we need to do now at this point is just add all those numbers up. Okay? So we got negative this, minus 2, minus 1.125, plus 2, plus 8.125, plus 18. Okay. All right, so if we add up all those numbers there, we get 23.625. And of course, if we take half of that, then of course that's going to be 11.8125 when we add it up there. Okay. And of course, for those of you that are wondering, in fraction form, that would be 189 divided by 16. And that's if you actually did it all by hand and didn't use the calculator. That's what you would get. All right, so now what we want to do is figure out what the exact area is under the curve of our function is from x equals 0 to x equals 3. Okay, and so now what we're going to do is a limit as n approaches infinity of the right-hand sum estimate. And so to do that, we'll need to write everything in terms of n to be able to do that. So of course, in this case, our delta x will just be 3 minus 0 divided by n now, since we're trying to stuff an infinite amount of rectangles in. So our width of our rectangles now will be 3 divided by n. And of course, the height of that would be whatever our function is evaluated at x sub I. And so our x sub I, of course, starts at 0 plus I times whatever delta x is, which is 3 over n. So we have this scenario. So therefore, our f of x sub I will look like this. It'll be 3i divided by n, all that cubed, minus 3 times 3i over n. And so that ends up being 27i cubed over n cubed minus 9I divided by n. And so this is what our function looks like. And of course, the height of our rectangle here will be characterized by what we see there. And so what we're going to do now is do the summation of this times the 3 divided by n, and we're going to evaluate the sum, and then after that we're going to take the limit. And if you notice, everything here for x, f of x of I, and for x of I as well, everything is written in terms of I for that, but the delta x here is a constant, and all that's written in terms of n. The point I'm trying to make is this. Whenever we do the summation first, the summation understands everything in I as its variable. So anything that has an n in it will look like a constant. Once we're done evaluating the summation, then for the limit, anything that's written in terms of n looks like a variable, and we'll be able to complete this procedure by doing it. So, first thing that we want to do is we need to figure out what is x sub I times delta x going to actually look like. So we know that the f of x sub I is going to be this. And all of that is going to be multiplied by delta x, which is 3 over n. And so if we go ahead and multiply the 3 divided by n into there, we will have, I believe it's 81I squared over n to the 4th minus 27I divided by n squared. And so now when we do the summation from I equals 1 to n, we're going to be doing it of f of x sub I times delta x, which will actually just be, can't get those equal signs to come out well. It's really going to be of all this. Okay, so this is all together here. So we know that per our summation properties, we can split this up into separate integrals, separate summations, and anything that does not have I in it is going to be looked at as a constant. So for this first term here, I could rewrite it as 81 over n to the 4th summation of I equals 1 to n of I cubed, and all that's on the inside, minus, now I have 27 over n squared summation of I equals 1 to n of just I. Okay? And so now from that point, if you watch my previous videos, you know that we have a distinct formula for the summation of the first n cubes, and we also have a formula for the sum of the first, when we add up the first n number of natural numbers. Okay? So we'll come here, rewrite all this, and now we know that for this portion here, this is just going to be n times n plus 1 times 2n plus 1, all that divided by 6. And then minus, say 27 over n squared times, and now for the summation of the first n natural numbers, it's just n times n plus 1, all of that over 2. Yep, so actually I need to come back here and erase this part because this is incorrect. I was reading that as the sum of squares instead of the sum of cubes. So that's a different formula. And for this one, the formula would just be n times n plus 1, all that divided by 2, and that is squared. Yeah. So the summation of the first n number of squared natural numbers would be what I wrote before. All right, so of course at this point, I'm just going to try to do as much simplification as I can. And we'll come here, say 81 into the fourth, and if we square this, we'll say this is just n squared times n plus 1 over n plus 1. And I'm going to write it like that because it'll actually benefit me to do so because of what we're trying to do with the limits later. So this is 27n squared. Of course, this will be still n times n plus 1 all over 2. And so here we know that this and this will simplify to just n squared. That will go to 1, and that will just go to n. So on our next step here, we'll just have 81 divided by 2, and this will be n squared over here, but we're going to rewrite it as n plus 1 over n times n plus 1 over n, like that. And then we'll say minus. We have 27 over 2, and then we'll write just n plus 1 over n. And then from that point, you can simplify a little bit more before we actually do our limit operator by rewriting this as 1 plus 1 over n. And of course, since we have 2 of them, that would be squared. 27 over 2 and 1 plus 1 over n, like that. Okay? And so now we have this in a form to where we could really evaluate the limit with ease at this point. Go ahead and fix that parenthesis there. So now we'll say the limit as n approaches infinity of this right-hand sum estimate here will really just be the limit as n approaches infinity of what we see here. Okay. And so now all we need to do is plug in, we just need to plug in infinities everywhere where we see n. So since I'm kind of running out of room here, I'll just go ahead and do that now. So everywhere where we see n here, I'll go ahead and plug in infinity instead. Of course, all that goes to 0, goes to 0. And so what we end up with here, just 81 over 2 times 1 squared, which is just 1, minus 27 over 2 times 1 plus 0, which is just 1. And so now, of course, 81 minus 27 would just be 54. And 54 divided by 2 would just be 27. And of course, this would be square units there. So if we actually looked at a graph of x cubed minus 3x, we would see that the net area under the curve from x equals 0 to x equals 3 in this case would be 27 square units. And here we know that if f of x is that, then of course this would factor out, and we could factor this out, and it would be x times x minus square root of 3 times x plus square root of 3. And saying that because now we kind of know what this function is going to look like. So we come here, that's negative square root of 3, and then that'll be at 0, and then here would be at square root of 3. We know that the end behavior looks like this: cross, cross, cross. So basic function looks like this, and we're trying to figure out essentially, let's try here, the area under the curve from when x is equal to 0, which is right here, to 3. So you know you got this portion that is below the x-axis, and you got that portion that is above the x-axis. Okay. All right, so now we want to move on to evaluating definite integrals by using known geometric shapes. And so for this problem, we notice that we have the definite integral from 0 to 2 of square root of 4 minus x squared. Now, if we notice here, if we take this function and we rewrite it like this, we notice that that is a circle centered about the origin that has a radius of 2. So if we were drawing all of this, this would be 2, that would be 0. And so we want to know what is the area under the curve of this function from 0 to 2. And of course, we know that that's a circle, but we're only considering the portion from here to here. So all this other stuff would have to go away. And so what we're left with this is the x and y axis here. All we're left with is this area that's under there. So, saying all that to say, we know that the area of a circle is pi r squared. And here, since we're only looking at a fourth of a circle, we could answer this just by dividing that by 4. And of course, in this case, our radius is 2. So we can just basically answer this by saying this is going to be pi r squared divided by 4, where the radius is equal to 2, and we just substitute 2 in. And we see that's just 4 pi over 4, which is pi square units. So whenever we know what the geometric shape is, for the function that we're given as far as the area under the curve of that function, then it's very easy to interpret what the definite integral is and thus compute it. Okay, let's go ahead and move on to the next example. All right, so for this example, I've already worked it out, but you see here that we're trying to basically find the area under the curve of the function y equals x minus 3 from when x is negative 1 to when it's 6. And if you notice here that since it is a line, we essentially made 2 right triangles. And we're trying to find the area of those 2 right triangles. And so, of course, we know that in general, the area of right triangle is 1/2 times base times height, where the x-axis here is considered our base, and our vertical length, where no matter whether it's above the x-axis or below, is interpreted as our height. So area 1 is just from x equals 1 to x equals 3, that right triangle. And we know that this right triangle is below the x-axis because the function y equals 3 has an x-intercept and x equals 3. And thus that's where it crosses the x-axis. So we compute area A1, where we have 1/2. The base is from negative 1 to 3, so that's a distance of 4. And the height goes from 0 to negative 4, so that's a distance of 4 as well. For the right triangle for area A2, we know that our base here is 3 again. Our height, in this case, is 3. And so, of course, it's just 1/2 times that. So once we put all that together, we use our property that says that, hey, if I'm going to interpret this area here that's below the x-axis, then I have to interpret it as being negative. And then on top of that, from 3 to 6, I know that that area is going to be interpreted as positive. So I just take the -8 square units and add it to the 9.5 square units, and I see that my net area is a -7.5 square units, or -3.5 units. So this communicates to us that we have more area under the x-axis than it is above the x-axis for the limits of integration that we were given. All right, so in this next example, we want to use the midpoint rule with the given value of n that we're given, which is the number of rectangles or the number of sub-intervals that we want to use to approximate the integral, or the, in this case, the definite integral or the area under the curve from x equals 1 to x equals 5. And we want to round our answer to 4 decimal places. So the note that I have below says that the midpoint rule says that if you use a midpoint x value between each sub-interval, okay, then you can use that for the height of your rectangles. And the example that I give, not what you're actually going to use in this problem, is from the previous problem. If we were looking at the interval from 0 to 3, and we were using 3 rectangles, then of course our delta x would be 1, because the b is 3, the a is 0, and the number of rectangles that we wanted is 3. And so here would be our traditional x value inputs. Now, since the midpoint rule says we have to pick something that is basically halfway in between each of these, then our x sub 1 would be halfway in between 0 and 1, which is 0.5. The next one would be halfway in between 1 and 2, which is 1.5, so on and so forth. Okay? So in this instance, since our x values is from 1 to 5, we know that our a is going to be 1 and our b is going to be 5. And we're asked to come up with, we'll use 4 rectangles here. So our delta x, which is b minus a divided by n, will just be 5 minus 1 over 4, which is just 1. Okay? And so also, we know that in this case, we know that our sub-interval here is going to be 1. So our x sub 0, in this case, is going to be 1. X sub 1 is going to be 2. X sub 2 is going to be 3. X sub 3 is going to be 4. And x sub 4 is going to be 5. Now, to find out our midpoint sample points, we know that in this case, x sub 1 bar is going to be 1.5. X sub 2 bar is going to be 2.5. X sub 3 bar is going to be 3.5. And x sub 4 bar is going to be 4.5. And so these are the x values that we are going to use to be able to calculate what our height of our rectangles are. Just to make sure that we understand here, each rectangle that we stuff under under the curve of this particular function here, that width is going to be a width of 1, and that length is going to be a height is going to be a length or height of f of x sub I. Okay? So moving on down here, you see that from that we have f of 1.5 that we need to find, f of 2.5, f of 3.5, f of 4.5 that we need to find. Okay? And so I'm going to rewrite our function here that we're trying to find the area under the curve of, just as a frame of reference. Okay. So now that we have that, let's get a little separation here. Scroll on down. So now, if I'm going to do midpoint estimate using, in this case, let's go back here, our n is 4, so we're going to use 4 rectangles. This is going to be the sum of f of x of I delta x from when I is equal to 1 to 4. And here I need to make sure that I notate this properly. This would be x sub I with the bar on it, letting us know that we're doing the midpoint. And so, of course, our delta x here was just 1, so we just have 1 times f of 1.5 plus f of 2.5 plus f of 3.5 plus f of 4.5. Okay. So now we can just calculate those values then. Come here to make some room to do that. So this is essentially just going to be whatever f of 1.5, 2.5, 3.5, and 4.5 are. Alright, so let's go ahead and calculate what these values are. So here, you see I've went ahead and I've typed in my function x squared times e raised to the negative x. My x values are such that I just need to go from 1 to 5 and 0 to 7 covers that, so I'm good. And all I need to do now is just evaluate the function at those various values of x. So I'm going to go to second, calculate value, and then we're just going to figure out what they are. Now notice that since we are putting this into the calculator is going to give us an approximation of what these are. So the value that we get is not going to be exactly what it should be, because of course e is an irrational number, and if we take an irrational number and raise it to any power there, we're going to be getting numbers that basically can't be written as a fraction. So your calculator is forced to give you approximations. Alright, so for the first one, if we type in 1.5, we get 0.50204.286. Do it for 2.5, we get 0.51303.124. We do it for 3.5, we get 0.36991.795. And if we do it for 4.5, we get 0.22495718. Okay. Of course, with that, you probably want to jot all those down. So in doing that, I'll just go ahead and list everything here, and then we'll give the total. So here we have 0.5020426 plus 0.51303.124 plus 0.36991795 plus 0.22495.718. Of course, all that's being multiplied by 1, so we really don't care about all that. And at the end of the day here, all this adds up to 1.5 60994,897, which just approximates to 4 decimal places, 1.6099 square units. Okay. All right, so in our next example here, we want to look at this function f of x, which is equal to x plus 1, which we know is a line, and we want to look at it from the values of -1 to 2. And we want to figure out, first of all, is the integral f of x dx as evaluated from -1 to 2, is it non-negative or not? And so we want to do this by first showing the sketch of the graph and interpreting the area. And then after we do that, we want to show the answer by calculating the definite integral by using known geometric shapes if we can. So first thing that we want to do is just sketch a graph of what x plus 1 looks like. And of course, it's a line that has a y-intercept here, and it kind of looks like this. And of course, we know that the x-intercept is going to be at -1, because if you plug in a -1 right here, we'll get 0. Now, on the other end, when this is equal to 2, which would be about right here, that would map up to a corresponding y value of 3. So that would be, just kind of out of proportion here. Go ahead and do it. So that's like 3 come down like that. And what we're concerned about is all this area that is in here. So from the graph, we see that it would be non-negative. So the area here is non-negative. And of course, I know area practically can only be non-negative, but we're just saying in terms of the graph. And so we see that it's non-negative. And so now the area that we have here is just a right triangle. Okay? So now if we wanted to figure out what the integral from -1 to 2 of f of x dx would be, we would just look at this as a right triangle where the area is 1/2 the base times the height, where the base is the length from -1 to 2, which is 3, and the height, which would be from the x-axis up to what the value of f would be if x is 2, and that would be 3. And so that ends up being 9/2 square units, or if you want to put it in decimal, 4.5 square units. Okay. All right, so looking at our next example here, we want to go ahead and use this property that you see right here, which is called our max-min inequality property from earlier in the video. We want to use this particular property. Looks like I got out of place there. We want to use this particular property to estimate the area under the curve of this particular function from this x value to that one, or put another way, the definite integral. So let's start off by looking at what square root of x looks like. And square root of x in general, I'll draw this over again, looks like this. And of course, we're wanting to consider it from 1 to 4, which, if we do this, will map us up to, let's say, this point right here, which that would be 1. And of course, this goes up to about here. And that maps up to 2. Can't get it to work right there. So we know that on the lower end, we would have a constant function of y equals 1 going like this. On the higher end, we would have a constant function of y equals 2 going like this. And so we know that the area under the curve that we're actually considering, which is all of this here, and of course, all that area right there, would have to be in between the areas that are created by the constant function on the low end versus the high end. Now, if we look at the constant function on the low end, that is just 1 here going from 1 to 4. So looking at that, that area would just be a length of, well, width of 3 and a height of 1. So that would just be 3 to this one. So we'll say the area of the lower and the area of the upper. This would be from 2 going from 1 to 4. So if we look at that rectangle, the area again, the base is going to be 3, but the height this time is going to be 2, so that's 6. So what we know on the low end is that can't be any less than 3, but on the high end, we know that it can't be more than 6. And so that's sort of what our estimate would be for the area under the curve. So for our next example here, see, I already have it worked out, but it's sort of the same thing. We look at this particular cubic function from 0 to 2, and we see that this is kind of what it looks like. And so here on the low end, we see that we have this constant function y equals 1, and we can find the area under the curve of just y equals 1. And then on the high end, we have this. So using that, the minimum area is going to be this rectangle that's formed by the base 0 to 2 and a height of 1, which is just 2 units. And on the max area, we know that, of course, it's the rectangle formed by the base of 0 to 2, which is 2, and the height of 5. And that's how we get 10 units there. So we know that we may not know exactly what it is, but we know that the actual area under the curve of x cubed minus 3x plus 3 is somewhere in between 2 and 10. All right, so the last thing that we want to do is be able to express the following limits as a definite integral on the definite integral. So remember how we were talking about how we actually went through the process of taking a Riemann sum and evaluating that, and then doing the limit of that to see what the actual value is, or the value of the area under the curve. But now we're looking at this and we're just saying, hey, let's interpret this notation here as a definite integral. And so if you remember, I had said that all of this is just representative of an infinite sum from whatever limits of integration that we have, which in this case would be from pi to 2 pi. And of course, our x of i's here is just the x values that we would plug in, and this delta x, if we are stuffing an infinite amount of rectangles under there, theoretically the smallest width I could have that's greater than 0 is represented by delta x. So that is why when we see this answer here, it would just look like cosine x divided by x of, taking the integral of that from pi to 2 pi dx. And so in knowing that, if we look at this next example here, then we see that if we're going to interpret this, this would just be infinite sum from 2 to 7 of 5x cubed minus 4x, and all that delta x. Or, sorry, dx, not delta x. And so that is what the definite integral would be interpreted to be there. All right, so for our next example, we want to look at this particular integral and interpret what the value of that definite integral would be. Here, if you notice that the limits of integration are equal to one another, so that's like us trying to add rectangles that have a width of 0. So we know that this particular integral's result is going to be 0. Okay. And of course, this last one here says, given that the definite integral of this function from 0 to 1 is equal to that, what would be the integral of this function where the limits of integration are changed? And so if you notice that with the limits of integration from a to b, we're assuming that a is always going to be smaller than or equal to b. But in this case, we have it in reverse, so that means we would have to interpret this as being the negative of what we would have here. So with all that said, it would just be the negative of the answer that we already have for this integral. Let's try to do that over again. That 8 didn't come out too good. Let's just try do it all over again. And of course, if we wrote that out and multiply it through the -1, then that would just be 8 minus 5 square root of 5 square units. And that's what that would be. Let's rewrite that.